Hello everyone, I am Paul Tarao and I will talk today about DeepLLM, which is a system that is casting dialog threads of an LLM into logic programs. So the objective of building DeepLLM is to automate step-by-step reasoning um, in an LLM dialog thread by recursively exploring alternatives or nodes and expanding details and nodes up to a given depth. We start from a single, very succinct, task-specific initiator, like a goal basically in Prolog or query, and we steer the automated dialog thread to stay focused on the task by synthesizing a prompt at each stage of the recursion that summarizes the depth first steps taken so far. We use semantic similarity to ground truth facts or oracle advice from another LLM instance to restrict the search space and validate the traces of justification steps returned as focused and trustable answers. And we have some applications to consequence predictions, causal explanation, why something is happening, the most usual step-by-step guidance to achieve a goal, topic-focused exploration of scientific literature, and supporting arguments for a thesis or a recommendation system for movies or songs. They all extract from the LLM's knowledge soup, step by step, just the essential information and not more that we need. So we don't have that very long trial and error dialogue that we usually have when using something like ChatGPT or Claude or Gemini, any of those LLMs. So the purpose is then to enhance interactions with large language models. We steer the LLM dialog thread by casting it into a logic program, basically a horn clause program. And dually, we also tweak logic programming for the LLM context. We aim to streamline information retrieval and interaction with the LLM. So we also address in a way the complexities of prompt engineering because the system does the prompting. It kind of adjusts dynamically what the prompt would be and filters the answers that come back and a few other steps. It also streamlines the user engagement with LLMs across various applications. So let me describe briefly the system architecture. So we have the user here, and we have the LLM with this little alien-looking face. And we have interactors that mediate the interaction with the LLM. There are recursors, the simplest interactors that just expand a given goal recursively and generate a horn clause program as a result that will be a horn clause program that will be then later given to a model builder. But we also can have refiners, and refiners could refer to ground truth facts or to alternative oracles that have a different opinion and validate what comes out from the LLM. And of course, we use an embeddings vector store. Information is retrieved by cosine similarity or L2 distance from this vector store when we want to see how close or how appropriate something is to the ground truth. Of course, we get answers back from this interaction, and we get also the synthesized logic programs. These are the output that can be later processed with other logic programming tools. So to summarize quickly the system components, we have active components. It's appropriate to call them agents because they have some kind of individual personality and mechanism of decision. They could be interactors, recursors, or refiners. So interactors manage the input prompt and break down the tasks. Recursors handle iterative exploration of the subtasks. And then the refiners enhance clarity and relevance of the LLM's responses. We have also the resources that I mentioned, ground truth facts, sentences collected from online sources or local databases or Wikipedia pages fetched from the internet, anything that we consider ground truth. And then the vector store, which enables this semantic search via the embeddings of sentences or concepts or noun phrases or chunks of sentences. Everything can be transformed into a vector, and distance between those vectors reflects reasonably accurately if the encoder is a very good one, an encoder that can come from the LLM itself, or it can come from another, let's say, BERT-based machine learning model. So let's look at the first examples. And that's the system's interface as well. So we have Streamlit app that's actually deployed, and it can be played with. I will give you at the end the links to that. It is deployed on the Streamlit cloud. So here we have some of the topics of interest that we could explore, like scientific concept explorer, consequence prediction, causal inference, and so on. When we click on activate the LLM, we start the interaction, and we get this exploration in the form of an AND/OR tree, or alternatively, if you want to see it as a horn-clause logic program. So in this case, we started with the goal artificial general intelligence, but curious about what's the LLM's opinion about that. And that's a scientific concept that we explore. It would tell us that this is about machine learning algorithms or cognitive computing capabilities or autonomous decision-making processes. And for each of those, we get then into the details. And you see here the AND node, and with prolog notation, that's an OR node with the typical marker for OR and the marker for AND in the horn-clause syntax. So each of them gets explored, and we have depth until a point where, of course, we want to stop the exploration. And we could also visualize the relation graph, and then we can browse it into a new tab. So those are user experience elements. So let's see how it looks. For instance, if we want to explore the relation graph, we have relations that are inferred, some of them are generalizations. They kind of explain the key concepts that you have seen in that logic program that we generate. And then the solver will be activated as well, and the logic program will generate its minimal model, which is everything that we can trust as being true as a result of this interaction. Everything that can infer in terms of rules and facts and action, propagation of the facts into rules, to have the unique minimal model of the Horn-Clause program. So this is the kind of propositional program that we get. I put it here in a very simple way. We need to kind of specify what is true in terms of facts, what is false, and then what are the rules here. And in this case, we get a very boring answer saying pet is true, but we actually have also the trace that brings us to it, basically the proof, the propositional proof, and that is displayed interactively if we want, or it's actually the encapsulation of the logic program as a trace. So DeepLLM is then basically logic programming, but done differently. SLD resolution's close selection via unification is replaced by LLM-driven dynamic close head creation with an option of focusing by proximity of embeddings to ground truth facts. As our dialogue units are sentences, the underlying logic is propositional. It is possible to extract, especially from GPT-4 and the latest LLMs, prologue code. It can write a very nice reverse algorithm or very simple prologue code from an appropriate user query. But sticking to propositional logic, because the LLM has been trained on trillions of sentences that were out there, and it's better in actually using natural language, which is a set of sentences that come out. And so that's where we are focusing on propositional logic. Moreover, by having the vector store, we have semantic matches that kind of replace unification of more complex logic formulas. And with that, we can accommodate the best way that the large language model can interact with us. So we have an API and the client side management, and the LLM's memory is based on the equivalent of a goal stack and a goal trace that records our steps on the current search path. Instead of variable bindings, answers are traces of justification steps clearly explaining where they are derived from. When the depth limit is reached, the items on the goal stack are interpreted as abducibles, statements that can be hypothetically assumed and then checked against integrity constraints. So we keep the ground truth in mind because we want truthful and focused stream of answers coming out from our automated interaction. Our depth-bounded refinement steps support compilation of the dialog threads to a Horn-Clause program to be explored with logic programming solvers later. We have modular, task-specific and customizable prompt engineering primitives that are aggregated together for n-step and or-step prompts. And we use normalized semantic similarity measures of embeddings that can be made available when, for instance, we want to generate probabilistic logic programs. Sentences in authoritative documents or collections seen as ground truth facts can be used to select abducibles via semantic similarity or advice of an LLM-based oracle. So overall, our approach exploits the synergies between structured prompt engineering, logic-guided recursion over LLM queries, and semantic search in an embeddings vector store. So all those together to simplify and streamline this interaction with the LLMs and automate it actually. So it's like a self-driving variant of LLM dialogue rather than the manual driving that we have when we go to ChatGPT or comparable other LLMs. Here is an example of a prompt template. So what we have is the AND component and the OR component. So this one is for causal reasoning. We need causal explanation in this context, and the context is described. It's usually the trace of interaction so far because we manage the memory of the LLM. Otherwise, it would be relatively boring if we give no context. But the context is actually built from the recursive past interaction. So it mimics very closely a longer multi-step chat that a human does. So the AND and the OR prompt. Now the OR prompter, expanding the head H in a series of alternatives, A1, AN, would generate this horn clause program, component of a program, and that can be more concisely expressed with the prolog notation for OR. The result of an AND prompter is, on the other hand, close head here, and the B1, Bn goals that to which H reduces. So when the depth limit is reached, the remaining unexplored goals are considered as abducibles. So they can be assumed and then rejected if the integrity constraints will fail on them. So the refiners are the ones that do that refinement process in which the abducibles are filtered with semantic distance to ground truth facts. And the refining decisions with the LLM-based oracles, we have two of them. One is a blunt true-false decider, and the other one is an LLM rater that basically returns a probability. So the model builder, we have also the execution mechanism that we want to have as part of the system. The system is implemented in Python, and we actually do not want to call a prolog system for that. And then there are a few problems with running this with prolog that are well known, in fact. Loops in the generated clauses would create problems with prolog's depth first execution model. And also satisfiability of propositional horn clause logic is in P. Actually, it's P complete. And there is even a linear graph-based algorithm by Donning and Gallier that's known for 30 or more years by now. So what do? We implement a simple solver that propagates truth from facts to rules. So implementing the model builder, well, given horn clause H is B1, Bn here, where all those Bi are known to be true, then we can infer from that that H is also true and can be added to the model. So it's basically the fixed point computation that gives the semantic of prolog. And if we have integrity constraints, which are horn clauses of the form false if all those are true, so that means that basically B1, B2, and Bn cannot be all true, because then the conjunction would be true, and that would imply false, right? So that would, as soon as they show up in the fixed point computation, we would remove them from, would acknowledge failure because there is a contradiction in the program. Or we could be a bit more lenient, and we could say that if the goal itself, the initiator that we started from, has been proven, even if there are contradictions elsewhere or later in the fixed point computations, we could accept that, especially because these are not always representing logic connections, but they could be associations or decomposition of tasks, and we do not have that level of precision that the strict logic semantics would necessarily require. But that's a choice that can be implemented depending on the application developer's preference. So we can stop as soon as a proof of the original goal emerges, assuming that contradictions far away are not affecting the result. There is also an alternative, which is not in the paper but is implemented actually. It's a torch-based GPU-friendly solver that's actually based on Sakama Inouye and Sato's tensor fixed point computation. And here is the link to it. So it's in a small file in the repository recursors called TenseLogic, and it takes advantage of GPUs, and for that we use torch implementation. It's just a few hundred lines. It's very simple. But complexity is not linear anymore because we work with matrices that are not sparse. GPU acceleration makes it practical for mid-size LLM-generated programs. And of course, future work, and this future work has been already explored in some of the newer papers by Sakama, Inouye, and Sato, is to work with sparse matrices, in which case you have very, very good scalability, which we didn't implement yet. Adaptation to work with vector embeddings, and soft unification is another possibility here. While soft unification is a weaker mechanism than equality in the propositional case, it would be close enough in terms of, let's say, cosinus similarity or L2 distance from the goal, and then the matching clause that is or fact that's pulled from the database. So the objective that we are wanting to achieve here is trustable AI, a requirement for wide adoption of today's LLMs in medical, educational, defense, and several other business applications. And it is also subject in the US at least of upcoming government regulations. So DeepLLM provides a principled approach towards trustable generative AI, oracles enforcing consistency and factuality, and then focused reasoning steps enforced by casting and/or steps into a propositional horn clause program that's verifiable on its own. So how DeepLLM enhances the user's LLM interactions? Well, it reduces the complexity of prompt engineering because the prompts are from our templates automatically generated. It automates the composition of tasks into simpler subtasks. It delegates that, of course, to the LLM to do the hard work. It refines prompts for more accurate user intent capture. it generates dynamic response for a wide range of queries, and improves user experience with concise and relevant information. As you have seen, we don't have that verbosity that you would, and sometimes hallucination that you would have when you have a, well, face-to-face interaction with the LLM in a chat window. So some future work here. Well, we would like to do some refinement in terms of granularity. One of them is to work with sentences and statements instead of those noun phrases that you have seen in the demo for the AGI that I showed early. Or actually lower granularities, SVO subject verb object triplets, which I've also seen a little bit, I also shown a little bit in the second demo with the graph, right? Those are basically SVO triplets. So question generators, asking LLMs to generate follow-up questions recursively. That's also out there, actually. It's not really future work. It has been done. That was a very exciting development where everything just kind of connected and went forward. Another thing is diversifiers and harmonizers. So to restrict the unwanted hallucinatory generation, we want to have diversifiers and harmonizers that can be expressed as additional integrity constraints. So what's a diversifier? No to all nodes are too close semantically. We want them to offer real alternatives. And the harmonizer is the integrity constraint that ensures that no to and nodes are too far semantically. They should go together, right? Implemented with semantic distances in the embeddings vector store. And some extended implementation techniques, fixed point computation with torch tensor that I mentioned that it's already working, and then extend the power of the underlying logic language. Answers that programming is a very good candidate for that, and also probabilistic logic programming. A new development that might make it to ICLP, we'll see that, is symmetric logic programming. That's a new design that I am basing on dual horn clauses, and this is already almost finished, and it would give you a symmetric view of the probability process on one side and the falsifiability process on the other side, and a combination of those two. So in conclusion, we are getting close to be out of time. Automation of step-by-step reasoning, LLMs functions as a de facto logic programming engine that mimics SLD resolution as they invent propositional horn programs. We have also the semantic similarity to ground facts, and we have a focused controlled output that enables deep investigations into details of specific scientific domains, and expert level causal reasoning or consequence prediction. As a result, we have a method to extract hallucination-free focused knowledge as a logic program. So thank you very much for listening, and here is a set of links that are also in the paper to explore the deployed systems independently. Thank you very much.